Alright, this is it. It is the general term of metallic sequence. Of course, we're gonna be talking also about Fibonacci sequence, a general term of Fibonacci sequence. So let us just recall last time we have denoted Vk, for example, as the powers of metallic ratio, or K, for example, and UK, the power of its conjugate, here UK as the power of its conjugate here, mu n minus power K. So denoted, of course, simply mu n power K, and also UK mu n minus power K. So in each case, we have a metallic ratio mu n plus C. So it's a different notation, UK, which is half of n plus square root n square plus 4. Okay, so its conjugate is gonna be, here we put with sum, it will be a difference. It's a negative number, mu n minus equal to half n minus, okay, this is negative square root of n square plus 4. Okay, so each one of these powers is a geometric sequence which verifies the relation Vk equal to here Vk verifies Vk minus 2 plus n times Vk minus 1. So UK also, it verifies the relation UK minus 2 plus n times UK minus 1 for some indexing K, which belongs to a set of natural numbers, and so on and so forth. Okay, so if we combine these two sequences, each of which is a geometric one, as we have previously indicated. So each one verifying also this relation. So we can combine them in order to get a metallic sequence. So by combining these two, C1 Vk, for example, plus C2 UK, for example, that's denoted by U index K. So this relation, this sequence, suppose we index it with K, for example, it becomes a sequence which we called it a metallic sequence. And in this case, it must also verify this recursive relation of recurrence verified by these ones, and this combination also is gonna be verifying the same relation, a similar relation, and that one is going to be, of course, it's going to be Wk is equal to Wk minus 1. This is minus, it's minus 2 here. It is minus 2 instead of uk minus 2 instead of uk minus 1. So here I have uk2 plus n wk minus 1. So this is a recurrence relation verified by every metallic sequence for any index in k, integer, positive, or greater or equal to 0. So in this case, this term it is now by its combination you have wk is equal to c1 vk plus c2 u. Okay, now by this combination, of course, you can obtain the similar relation if we consider this equation as this relation as defining every metallic sequence. Now, from this, we can solve it by different method, especially with the difference method. We can apply it to this equation because this indexing it belongs to a set of natural numbers, including 0. So we are going to obtain a similar relation for the general term. This is the general term. For some C1 and C2, which are real numbers. Now, so now from this general term form, so we can determine the coefficient C1 and C2 subject to some initial condition. So we can take initial condition as u naught, u0 equal to 0, and u0, u1 equal to 1, for example, as it is the case for Fibonacci sequence, the usual one, the simplest case. So it starts with 0 and 1. And then we are going also, this does not, it is not necessary to always start by 0 and 1 as initial condition. We can also start with some different initial conditions, some real number, suppose A, W1, suppose B, also it can work. Now these initial conditions will lead to the general form of this sequence, especially this one, this general term. Okay, so now let us try to use, suppose these ones. Okay, let us use this general form, general initial condition here, and we can determine this the constant C1 and C2, for example. So in this case, we are going to consider Vk as this one, this metallic ratio power k, and also uk. This will be, as you have indicated at the beginning, it's going to be equal its conjugate n power k. Okay, so now we can use the initial conditions here, so which means that if I consider the general case with k equal to, so first of all with k, wk, so equal to c1, so vk being mu n plus n power k plus c2 uk is 1 mu n minus power k. Just to simplify the notation for the the conjugate of the metallic ratio, and here metallic ratio. So there are different notation. We don't care about it for this moment. And then this index goes with these powers, and then we can use the initial conditions here. Using these initial conditions, we can have Wk if k equals 0, so we have C1, so mu n plus c power 0, C2 mu n negative power 0. So one condition, another condition is W1 is C1 mu n power 1. So we don't care about when the power is 1, no problem. Plus C2 equal mu n power 1. Okay, so power 1 here in this case. Now, this being equal to W, so we may have this is A, and constant, especially different from 0 or equal to 0, but B is going to be another real number, especially which are positive. So we have C1, so any number different from 0 power 0, it's going to be equal to 1, so plus C2. So also this power leads to 1. So now we have C1 here, so mu 1 mu n plus C2 mu n minus. So this so now we have to solve this system here. So the system, and it is linear in the coefficients C1 and C2. So now in this case we can use the general method, which is substitution. Suppose C2 equal to, so C2 here can solve for it. We can eliminate C2 out of this system, and it is going to be equal to A minus C1. Okay, now in the second equation, we have C1 mu n plus C plus, now C2 we substitute by its value A minus C1 times mu n minus, in this case. Now this must be equal to B, so let's put B on this side. And now we have to solve for C1 in terms of the metallic ratio and its conjugate. So what we are going to have here, it's going to be C1, and it will involve metallic ratio and its conjugate mu n minus, and then on the other side, this one times the conjugate on the other side is gonna be minus A times mu n minus, in this case. Okay, so now we can find the value of C1 clearly is equal to the ratio B minus A mu n minus over the difference mu n plus C minus mu n minus. Okay, so we can put this one in the form, so mu n plus C. Oh, okay, so we need to find C2 first of all, and second of all, so we have to find C2. So C2 here is going to be, so we know it is A minus C1. So C1 we know it, and then we get A minus this quotient B minus A mu n minus over mu n plus C minus mu n minus. Okay. So this is value of C2. So we can rearrange terms in order to get A mu n plus minus mu n minus C plus C or minus B minus A mu n minus here in this case over the same denominator minus mu n minus in this case. Now what you have here, so we can see that some cancellation may apply in case okay, this term cannot be cancelled, but we can see that this one and this one negative, this one positive, so they will cancel. This one will cancel with this one, and then I'm left with C2 is equal to so A times mu n plus C minus B over, and now the same denominator as in the other case. So we have so C1 is here and C2 is here. We have these constant, and here we can now find the general term given by C1 times this power plus C2, which is this quantity times that power. That is a general form of metallic sequence that can be written in this case as here we have the general term is C1 is A mu n plus minus B over R. So we need more space over here. So we have finally the general term is this C1 here, B minus A times mu n minus over mu n plus C minus mu n minus, so times the power of mu n plus okay plus this C2 A mu n plus C minus C B over now the difference mu n plus C minus C, its conjugate mu n plus negative, okay, times the power of the conjugate mu n negative power k with k, with indexing with k being either 0, 1, 2, 3, and so on and so forth. So here and n here must be n here must be a fixed integer, which is greater or equal to 1. In case it is equal to 1, of course, we're going to have a Fibonacci sequence. Okay, let us see what does it look like if we set the condition like 1 for Fibonacci WK with k equals 0. So if it is equal to 0 and the condition W1 equal to 1. Okay, so this case is w1 is equal to 1. Okay, so this is to be reads with n equal to 1. So we consider two cases, n equal to 1 or n equal to 2, for example, and so on. In which case, with n equal to 1, this is a golden sequence, and n equal to is the silver sequence. And in most general case, so these golden and this silver, they become other general golden sequence or general silver sequence. Okay, so now in the case wk equals 0, so we have if it is equal to 0, so we will have here a, this is a, here, so, and this is b. Okay, so b here and there. So in that case, the general term is gonna be equal with b equal to 1 minus a mu n. Okay, a is equal to 0. A is equal to 0. So we're gonna have this term with 4, and we have mu n plus minus mu n minus and mu n power k plus c. This one is going to be equal to 0, mu n plus c minus b equal to 1 times the mu 1 here, 1 divided by, okay, here mu n plus c minus mu n minus, of course here we need to multiply by mu n minus power k. So it is this this form we are going to have, and it will simplify. It will simplify to wk equal to 1. So here 0, we're gonna have 1 over mu n plus c minus mu n minus c, mu n plus k power k, so plus c. Here we're gonna have minus 1 over mu n plus c power, not power, of course power 1, if you say so. Mu n minus, so times mu n minus power k. So finally, so we get, so let us use this one. This will be a simplified general form as compared to this general form. This is one the simplest case. It is now here there will be 1 over mu n minus mu n minus c. So it is common except have a negative here. So times the mu n power k minus mu n minus power k. Okay, so this is what we are going to have as for the simplest case where a is equal to 0 and b equal to 1. More specifically here, we are going to express this ratio in terms of n. So we are going to have, this is going to be, okay, wk equal to, so this difference is going to be mu n plus minus mu n minus c is half of n plus c square root n square plus 4. Now minus c again half of n minus square root n square plus 4. Okay, so in this case some cancellation applies. To apply on n. Okay, now the square root will double, and this one plus this one is going to be equal to, finally, it's going to be equal to square root n square plus 4. Now, as it is in the denominator here, so it is power negative 1 here, power negative 1 here, power negative 1 here. We can rationalize the denominator because that one is 1 over square root n square plus 4. By rationalizing the denominator, so we are going to have this square root of n square plus 4 divided by n square plus 4. Okay, so this on y we have square root of n square plus 4 divided by n square plus 4. Now times z. Now here we can have a half power k here. Is let us take n plus the square root of n square plus 4 power k. So minus its conjugate, n minus the square root n square plus 4 over 2 power k. So now this becomes the general term of the metallic sequence in case the initial conditions with initial condition A equals to 0 and B equal to 1. Now, if we take, for example, a different condition, excuse me. In this case, if we take, for example, okay, let us take, if we take A equal to 2 and B equal to 1, so we obtain a metallic sequence known as, in this case, it's going to be equal Lucas sequence. Lucas sequence. In case the fixed integer n is equal to 1. So it is kind of generalization of Gordon sequence. The Gordon sequence becomes the Lucas sequence in case initial conditions are taken to be A equal to 2 and B equal to 1. Now let us see how it will look like in case if we use n equal to 1. So Lucas sequence, how it will look like. Lucas sequence. Now let us call it LK. So we don't need a general form because it will be very simple to calculate. Since we take initial term being 2, the second one being 1. So because this is W0, W1, W0 equal to 2, W1 is equal to 1. Now we can continue, or either we use this relation or we use this one. The current relation, we take this one plus this one is going to be equal to 3. Sum equal to 4. Sum of these equal to 7. Sum of this equal to 11, and so on, until we get a general term WK, which is subject to the condition B equal to 1, A equal to 2. Okay, so now in case n equal to 2, and suppose 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 n equal to 2 and a equal to 1 and b equal to 1. So in this case, we get another form of Pell sequence. Pell sequence, another form. So with the initial condition, let us call it PPK. So with the initial condition, a equal to 1 and b equal to 1. So remember n equal to 2. So now either we can use to find general form with a equal to n equal to 2 and a and b both equal to 1, or we can use the recurrence relation also to find that we're going to get this term times the 2 and plus 1 is going to be equal to 3. Sorry, let me use the same. This is 3. Oh, this is 3. Yes, let me use this one. And this times n is going to be equal to n times 3 times 2 is 6. 6 plus 1 is going to be 7. And 7 times 2 is going to be equal to 14. 14 plus 3 is going to be equal to 17. And so on and so forth. So, but if we use this form with initial condition not equal to with a equal to 0 and b equal to 1, we get another pairs sequence also. Pairs sequence again, which is made up of what is generally called pairs numbers. So in that case, we can use this one with n. To find this one, we can use the n equal to 2. So we are going to have a situation like this. Another pair equation, I call it qk, sorry. And the first term is 0, second term is 1. These are the initial conditions. And then we can use this general form with n equal to 2. So by doing so, of course, we're going to get n square is equal to 4. 2 power 2 is equal to 4, plus 4 is 8, square root 8. Now divide by 8 is going to be square root of 2, so over 4. Because here we are going to get this quantity. It's going to be square root of 8 over 8, and it is 4 out. It's going to be 2. Square root 2 divided by 8. It's going to be equal to square root 2 over 4. Now inside here we have n equal to 2 plus the square root of 2 times square root of 2 times 2, and if you divide by 2, it's going to be equal to 1 plus the square root of 2. On the other hand, so okay, so minus that one is going to be equal to 1 minus square root 2 power k. So now we divide by so here it is 4, divide by 4, and you multiply by square root 2. So over 4, say. Let us remove this one here. So now with v k equal to 0, of course, we're going to have 0. We're going to have 0. And now with k equal to 1, we are going to have 1 will cancel, 1 and 1, and the square root 2 will double and multiply. The 2 square root 2 square divided by 4 is going to be 2 over 2. It's going to be 1. Now, if we continue, we find the pairs numbers here. I use this color with the k now equal to 4 to 3. So this is the W0, W1, W2, k equal to 2. So we're going to have WK2 is going to be square root 2 over 4 times 1 plus square root 2 power 2. Now minus 1 minus the square root of 2 power 2. Okay, so in this case, what you are going to have is going to be now this indication, this becomes qk, so that one is the same as qk, q2. So q2 here as a general term is going to be square root 2. So square root 2 over 4. Now here we have 1 plus square root 2 power 2 is going to be 1 plus 2 plus twice square root 2. Now minus here I have 1 plus 2 minus 2 square root of 2. Okay, in this case we are going to have square root 2. Now so these real numbers, these integers will cancel, and these square roots will double. So we'll double to 4 square root 2. And in this case, we are going to have to simplify and get square root 2 power 2. In this case, this one power 2 is going to be equal to 2. Okay, so Q3, which is here W3, so it is square root 2 over 4, 1 plus square root 2 power 3 minus 1 minus square root 2 power 3, and so on. And what you are going to get as the current relation here becomes easy to work with, except for getting the general term here. So it is going to be 2 times 2 plus 1, which is going to be 5. After calculation, you're going to have 5. The next one is going to be 5 times 2 is 10, 10 plus 2 is going to be 12, and so on, and so forth. And these are pairs numbers as compared to these ones, which are a general form when starting with the initial condition A equal to 1 and B equal to 1. We have these numbers where white A equals 0 and B equal to 1. We're going to have these other numbers which are specifically what is called pairs numbers. Okay, so so here we have come to this number is equal to 5 after calculation with k equal to 3. Okay, so this is it for today. We have the general form, a general term of metallic sequence, which is given by this expression, and so we shall call it a day here, so that we continue next time. In another video, we are going to look for other forms of this metallic ratio which appear in the metallic sequence. So next time.